From this session, we are going to discuss about the chemical reaction engineering. According to the GATE syllabus, our outline will be the basic understanding, then interpretation of batch reactor data. Next, we will go for understanding the ideal single reactors like CSTR and PFR, which will be followed by the performance analysis of CSTRs and PFRs in series and parallel. And after that, there will be idea, these concepts of the space-time optimization and batch time optimization for multiple reaction. Next, we will discuss these catalytic reactions and the detail aspects, and that will be followed by this residence time distribution analysis and some additional topics which we will be discussing later, right. So, that is the broad overview of what we are going to learn in reaction engineering. So, to start with, it is very essential to classify the reaction, right. So, how we can classify? Definitely we have not defined the rate equation. So, based on the rate equation we are not going to classify, but this is a broader different classification based on the number of phases present in that system and based on the fact that whether it is a catalytic reaction or a non-catalytic reaction. So, you see, reaction engineering, we start with classification of reactions, right. So, the first classification is based on the number of phases present in the system. So, we will have homogeneous reaction or heterogeneous reaction, and simultaneously we can also classify the system of reaction based on whether we are using catalyst, right. So, accordingly we will have catalytic reaction and non-catalytic reaction. So, you see that we have got 4 division here. Catalytic, or rather homogeneous, non-homogeneous, and here non-catalytic, catalytic. So, homogeneous non-catalytic reactions, we can have most of the gas phase reactions are non-catalytic homogeneous reaction, right. So, this is most of the gas phase reaction, and also fast reactions like burning of flames, etc., which is also a gas phase reaction. Now, non-catalytic non-homogeneous reaction, right, or heterogeneous reaction. Okay. So, it is burning of coal, roasting of sulfur, etc. Now, catalytic homogeneous reaction, we can have this enzyme substrate kinetics, colloidal reaction, which can be fairly approximated as homogeneous. So, these are homogeneous catalytic reaction, and non-homogeneous, let us say ammonia synthesis, sulfur trioxide synthesis, etc. Right. So, that is a very broad perspective classification of the different reactions what we encounter in process industry. Next, immediately once we have classified, next question, how to represent the rate of the reaction. See, in any reacting system, say A giving product, so it is a single reactant system, we have minus of dNA dt to be positive as Na decreases with time. We are writing it for the dissipation rate, right. So, we can, if we write the product is P, so we can alternatively write dNP dt, which is the rate of formation of P. That is also an equivalent expression of the reaction rate, but generally we prefer to write it with respect to the reactant. Okay. However, you see that this depends on some extensive property of that system, where Na is the number of moles of A, right. So, if you increase the volume, it will increase volume of the reactant or volume of the reactor, right. If it is a catalytic reaction, if you increase the catalytic loading, that this dNA dt is increasing, right. And if it is an interfacial reaction, if you increase the surface area, right, then definitely dNA dt will be increasing. So, the point is you must define some specific reaction rate. Okay. It is not the simply the rate of the reaction, it is the specific reaction rate, such that the reaction rate of one system and the reaction rate what we found from the some other condition remains identical, right, or expression wise they must be identical. So, this is an extensive property. We have to convert it to a specific property such that the rate expressions are comparable. Right. So, point is how we can make these rate expressions comparable. We have to divide, we know just like mass is to be divided by volume. Mass is an extensive property, volume is an extensive property. If I divide, we will get the mass per unit volume density, that is an intrinsic or specific property. So, here this is an extensive property, so we must divide it by another extensive property which is pertinent to this reaction, right, and from there we can generate a specific reaction rate. So, this gives the idea of specific reaction rate. So, minus Ra minus of 1 by V dNA dt, where V is the volume of the reactant. So, it can be written as minus of Ra prime, here the basis of this extensive property with which we are normalizing, that is changing, and here when it is prime it is W. W is the weight of the catalyst, right. So, this is a different basis. So, definitely minus Ra prime and minus Ra are not same. So, if it is an interfacial reaction, it may be minus of 1 by S dNA dt, where S is the interfacial area and minus of RA triple prime minus of 1 by VR dNA dt, where VR is the volume of the reactor. Okay. So, based on this idea, we can write that from here we can write what is the equation relating RA to RA prime to RA double prime and RA 4 prime. So, it is obvious that minus of RA into V minus of RA prime into W minus of RA double prime into S and minus of RA triple prime into VR. So, by this we can compare and can write this relationship between minus RA double prime, minus RA prime and different other rate expressions. So, next you see that we will now going for the reaction rate once again, but not definition. If I have multiple reactants and products, what will be the rate expression? Here we have discussed it as if this is only valid for only one reactant and one product. But let us have this. Where A, this is a balanced chemical reaction where small a and small v, small r and small s are stoichiometric coefficients, where the capital A, B, R and S, they are the chemical formula of the reactant and the product which are involved in this reaction, right. So, if I go by minus RA, it is minus of 1 by V dNA dt. Now, you see that delta Na, or rather we can write dNA with a minus sign is equal to minus RA into V into dt, right. So, if I integrate this, I will get that okay, how this number of A is changing with time, right, for a fixed or variable volume. Now, the point is what we have to note, A moles of A reacts with B moles of B, right, small b moles of B. So, minus of dNA by A must be is equal to minus of dNB by B. So, if I divide it by delta t and put a limit delta t tending to 0 and also by 1 by V multiply it. So, what you will get? Minus RA divided by A is equal to minus RB divided by B, and this is equal to dNR by R is equal to dNS by S. So, obviously it is RR by small r is equal to RS by small s, where RB is minus of 1 by V dNA dt, RR 1 by V, there is no minus sign because NR is increasing with time, and RS 1 by V dNS dt, right. So, this is a very important relation what we have to note. Now, you see we have defined what is the specific rate of a reaction. Next, definitely we have to think about that how it can be related to measurable quantities like concentration and temperature. So, our objective here is to relate this specific rate to the concentration of the species involved and definitely on temperature. Why temperature is so important? Because reaction between A and B is facilitated by the collision of A and B molecules. So, this collision we know from kinetic theory is dependent on temperature, right. So, concentration and temperature dependent rate expression. So, you can understand that if it is a reaction A plus B giving product, that minus Ra must be a function of Ca, Cb and T. So, what is that function? How we can theoretically justify the respective functional form here on the right hand side, that we will discuss later. But before that, let us also, based on this representation of the reaction, let us classify the reactions, right. Classification of reaction based on stoichiometry. Stoichiometry and rate equation or rate. So, first classification is single and multiple reactions. So, you see single reaction is A giving R, right, 2A giving 3B, etc. That is, the reaction or the system, or rather the system is described by a single chemical reaction. So, that is a single reacting system. Now, in multiple reaction we have definitely series reaction, parallel reaction. We can have series parallel combination as well. So, series reaction, its easy example is A giving R giving S, right. There is an intermediate which is giving you finally the product A, this S. And parallel, again it is classified as competitive side by side. So, competitive parallel means there is two parallel pathway from A giving R and S, and side by side is A giving R, B giving S. So, this is also a parallel reaction, but it is non-competitive, but rather it is a side by side. Now, if I write A plus B giving R, R plus B giving S, example. Right. So, this reaction is in series with respect to A, R and S. And competitive parallel with respect to B, right. So, that is the basic, very basic classification of reaction based on the stoichiometry, because we are focusing only here not on the rate equation, but only on the stoichiometry of this chemical reaction, right. Now, if I focus on rate, see, first let us discuss about this functional form, right. So, what will be this function where the reaction is A plus B giving product? Now, we can say that minus of Ra is proportional to the rate of collision between A and B. Right. Now collision is dependent, the rate of collision, see, when we will say that they will collide, here we have A, here we have B, right. So they must collide like this, AB. Now there are also possible other combinations like AA, binary combinations, BB, right, etc. There may be 3-body combination AAA, ABA, etc. Now out of that, only AB collision or AB simultaneous presence at a location give rise to reaction, right. So this, the probability of finding A and B, right, is proportional to the respective product of the concentration, or it's proportional to, rather we will say PA into PB, or it's equal to PA into PB, and that is proportional to CA into CB. So this functional expression must include a term CA into CB, and temperature term, temperature dependence is separable from concentration. So you can write that minus RA is some constant or a function dependent on temperature into CA into CB, and this we call rate constant, right. So that's the scheme of representing a reaction. So evidently, if I think of reactions A plus or AA plus BB giving product, we can write that minus RA is equal to K into Ca to the power A, Cb to the power B. That's A molecules of capital A and B molecules of species B, they must be together and they will react. So this is the rate expression, right. However, in many cases, they experimentally determined rate expression. We will see how we can determine these experimental rate expressions. Does not match with the aforestated form, right. That is, minus RA is not at all can be represented by Ca to the power alpha B, Cb to the power B, but rather as an example it may be K1 into Ca to the power alpha divided by Cb plus K2 into Cb to the power beta, something like that. So the rate expression doesn't match with the typical form along with the added stoichiometric coefficients. So if this happens, this type of situation arises, then we will refer this sort of reaction as non-elementary reaction. And this one is elementary reaction. Right. Just like the typical example, is H2 plus Br2 giving 2HBr, and it is a photoactivated. Now you see what actually happens. Bromine, upon absorbing this H nu, breaks down into two bromine free radicals. This attacks H2, giving HBr, that is the product, plus hydrogen free radical. Hydrogen free radical may react with bromine again, giving HBr plus bromine free radical, and H dot plus Br dot again reacts to form HBr. So overall, you see, this H2 plus Br2, it will not match with this typical stoichiometrically consistent rate expression, that is minus of R H2 is equal to concentration of H2 into concentration of Br2. But actually the rate expression of RHBr is equal to K1 concentration of H2 concentration of Br2 to the power half divided by K2 plus concentration of HBr by concentration of Br2. So it is not at all consistent. So this is not inconsistent with the stoichiometry. Right. And because, why it happens? Because it is a non-elementary reaction. Because it is a non-elementary reaction. So basically, what is the reason? The reason is obvious in this example. You see that actually it involves lot of reactions, intermediate reactions, which finally leads to the product, right? So individual reactions here, whatever we have listed, understanding the mechanism, they are elementary reactions. But as this Br dot, H dot, these two specific species, they are highly short-lived, right? Highly reactive, because they are formed and immediately they are consumed by another. So its presence, it's very, very difficult to detect using the conventional analytical devices. And as a consequence, what we record from a general physical observation is H2 plus Br2 exposed to this or given some this light of appropriate frequency will immediately give rise to HBr. So the point here is that non-elementary reaction is actually a combination of multiple elementary reactions. Is a combination of multiple elementary reaction that involves active components. And these active components here, the example is free radical, which is highly reactive. So how to formulate the rate expression of a non-elementary reaction, that specific topic we will take up later. But before that, we will proceed with further understanding of this rate and some of the parameters associated with this reaction. So we have got the classification as single reaction and multiple reaction. In addition to that, we have also discussed about very basics of elementary and non-elementary reactions. Now you see, here we will introduce another two terms which are called molecularity and order. Molecularity is what? number of molecules taking part in a reaction, right, and it will be less than or equal to 3, always an integer, and the definition is only valid for elementary reaction. Non-elementary reaction we cannot define molecularity. Right. So, the number of molecules taking part in the reaction, set A plus B giving product, if it is elementary reaction, it is a bimolecular reaction. So, two different molecules, they are taking part in the reactions. Okay. Value is 1, 2 or occasionally 3. Note that molecularity refers only to an elementary reaction. On the other hand, if I have a reaction AA, BB giving product, and the rate expression minus RA is K Ca to the power alpha, Cv to the power beta, Cc to the power gamma, etc., etc. Now, see, alpha may not be equal to A, beta may not be equal to B, gamma may not be equal to C here, right. So, this is a reaction rate which has nothing to do in general with the reaction stoichiometry if it is not an elementary reaction. So, this definition of rate is valid for elementary as well as non-elementary. If it is an elementary reaction, alpha will be A, beta will be B and gamma will be C, right. So, the order is the specific exponent. Order is the exponent of concentration terms in the corresponding rate equation. So, order is alpha with respect to A, order is beta with respect to B, order is gamma with respect to C, and overall order is alpha plus beta plus gamma, let it be equal to n, right. So, order can be a fraction. Order may or may not be an integer. It may be a fraction and the definition is valid for elementary as well as non-elementary reactions. So, that is the definition or difference of order and molecularity, right. Next, we will specifically focus on the units of rate constant. Let us say this is K, just the previous example. So, it is K into C to the power n. So, concentration term raised to the power overall order, right. So, minus RA, what will be its unit? Mole per meter cube time. Its dimension is this, dimension of K and mole per meter cube to the power n. So, K, this C this is concentration term and this is also concentration. Concentration we can also write differently. So, unit or dimension of K is concentration to the power 1 minus n into time inverse. So, first order it is only time inverse, second order it is just like concentration to the power minus 1 time to the power minus 1. And similarly we can find out the third, fourth order terms, right. Now see, instead of concentration for gas phase reaction in specific, we can use the partial pressure as well. You see, alternative to concentration based rate expression. So, here we can have partial pressure. And what is the relation? Say we have PV, let us say it is ideal gas, nRT. So, by definition of partial pressure, it is Pi into V equal to Ni RT. So, Pi, which is Ni by V RT, is equal to Ci RT. So, concentration Ci is equal to Pi by RT. So, minus Ra, whatever we have written, Kca to the power alpha, Cv to the power beta. Let us say it is A plus B giving product. So, from here we can write that K into Pa to the power alpha, Pb to the power alpha divided by RT to the power alpha plus beta. So, this we can write as K prime into Pa to the power alpha into Pb to the power beta, where K prime is equal to K divided by RT to the power n, where n is the overall order of the system, right. So, we can write that. So, let us focus more on the elementary rate expressions. So, there are some specific points which we have to understand, rate expressions for elementary reactions. Let us focus on elementary reactions first. See, A giving R, if it is elementary, we can write minus Ra is equal to Kca, rate constant is K, right, which is obviously equal to Rr. Now, if I alternatively write 2A giving 2R, the rate expression will not remain same. It will be minus Ra is equal to, say it is K1 into Cs square, right, K1 into Cs square, and that is equal to Rr. Why? Because 2A giving 2R, so A giving R. However, if I write 2A plus 3B giving 5C, and the rate expression for A minus Ra. Minus Ra is equal to Ka, it is with respect to A, Ka into Cs square into Cb cube, right. Now, minus Rb is equal to, we can write Kb into Cs square into Cb cube, and plus Rc is equal to Kc Cs square into Cb cube. Now, we know that just we have discussed initially, minus Ra by 2 is equal to minus Rb by 3 is equal to Rc by 5. So, Ka by 2 is equal to Kb by 3 is equal to Kc by 5. So which means if I am writing it with respect to A, we will write minus Ra is equal to Ka Ca square Cb cube minus Rb is equal to, now in terms of Ka, what is Kb? 3 by 2. So 3 by 2 Ka Ca square into Cb cube and plus Rc is equal to 5 by 2 Ka Ca square into Cb cube. So that we have to keep in mind always. There must be a stoichiometric parity with the rate equation, and we must note that with respect to which component we are writing the rate expression. Generally we write it in terms of the limiting component, but there is no hard and fast rule that we always have to write it with respect to the limiting component. Okay. Now next so these are the rate expressions of elementary reaction. So for non-elementary reactions we have stated that a rate expression of a non-elementary reaction cannot be directly derived from the stoichiometry, the overall stoichiometry. We must have some method by which we can calculate it. So what is that? What is the method that we are going to discuss right now? But first we have to understand the pathways of non-elementary reaction. So you mentioned that non-elementary reaction is a combination of appropriate elementary reaction, and the chemist will give you a tentative scheme of that reaction, right, and from which we have to validate that. So how we can validate it? So point of the topic is kinetic model of non-elementary reaction. Right. So non-elementary reaction, as I mentioned, it a combination of elementary reaction including active components or active species, right. So what is that? Let us say the reaction is A2 plus B2 giving 2AB, right. So the rate expression, if it does not match or it is not minus Ra2 is not equal to this K into Ca2 into Cb2, then we have to think about this possibility of this reaction to be an non-elementary reaction. And we can propose a mechanism like A2 is going to give you 2A star, where A star is the active component which has got a very short life because of its very high reactivity. Now A star plus B2 giving AB plus B star, and finally A star plus B star giving AB. So overall it is a reversible sort of reaction, and this is the overall reaction. And this is the mechanism. Now question is whether this mechanism is correct or wrong, right, that we have to justify through quantitative analysis. But before that, just a bit of chemistry, we have to note that, or we have to understand that what are the typical examples of active components. First, just we have mentioned free radical. So these active components are highly reactive and short-lived. Second, it may be ions. Third, it may be molecule which are highly reactive. Right. And fourth, we know it is the transition complex. Right. So just like benzene ring, where it is reacting with some electrophilic positive polarity compound, so this electron cloud in the benzene ring will attract this, right? So this is a typical example of transition complex, which will further stabilize by electronic rearrangement and will give you the product something like this. Okay. So these are the examples of active components like free radicals, ions, molecules and transition complexes. So free atoms are larger fragments of stable molecule that contains one or more unpaired electron of the free radical. Typically we know ions, molecules, right, and transition complexes. So non-elementary reactions, we can have classifications also. First one is called non-chain reaction. So what is the mechanism? Reactant, active intermediate, active component or active intermediate also. Right. So we use this reactant, intermediate, giving product. The typical example is enzyme substrate, kinetics. Enzyme, it combines with the substrate, giving enzyme substrate complex, which is the active intermediate. Now it rearranges itself, giving the free enzyme and the product. Right. So that's the first example, which is called the non-chain reactions. Second example is the chain reaction. Reactant, active intermediate, active intermediate, plus which reacts with more reactant, giving product and regenerate the intermediate. Now this intermediate finally leads to product. Right. So this is called initiation. This is the propagation, and this is termination step. Right? The typical example which we have just cited, that reaction of hydrogen and bromine. See, Br2 on absorbing H nu giving 2 Br dot. So, this is initiation. Now, Br dot plus H2 giving HBr plus H dot. So, H dot is the intermediate, HBr is a product. So, propagation. Now, Br dot again H dot reacts with Br2 giving HBr plus Br dot. That is also propagation. And Br dot plus H dot giving HBr, that is termination. Right? So, this is a typical example of chain reactions. Now, that is the classification part of non-elementary reaction. So, you have to think of the method by which understanding or knowing the reaction mechanism, right, or having some tentative reaction mechanism, we can generate the rate expression and check whether the actual data of the system tally with that derived rate equation, right. So, we have to derive the rate equation knowing some reaction mechanism, just like I have mentioned here. So, you see, developing the rate expression from the reaction mechanism of a non-elementary reaction. The first model, which is called the pseudo-steady approximation. What is that? As the basic logic is, as the active intermediates are highly reactive, we consider concentration is close to 0, right, where X is any active intermediate, right. So, dx dt, its rate of change of concentration with time, we consider it to be 0. So, its rate of formation or rate of dissipation of all active intermediate must be 0. So, that is the pseudo-steady approximation. Second, it is specifically valid for homogeneous catalytic reaction. Let us say C plus C plus X giving Cx. Just like example is enzyme plus substrate giving enzyme substrate complex, right. Let the initial amount of catalyst is C naught. So, C naught is equal to concentration C naught is equal to free enzyme plus the enzyme substrate complex, this is 1, and we assume, this is the assumption, instantaneous equilibrium, that is K is Cx by C into X, right. So, this is a typical methodology we use to derive the Michaelis-Menten kinetics, though I am not going to discuss it right now. But the point is, Michaelis-Menten kinetics is also derivable from pseudo-steady approximation. So, we will focus mostly on this, right, and from there we will try to derive what should be the tentative rate expression for a non-elementary reaction, provided we know a mechanism. So, it is a pseudo-steady approximation based on which we will work, and I will solve a problem and we will try to show that why the pseudo-steady mechanism is so important. So, you see, the problem here gives that we have degradation of nitrogen pentoxide N2O5, finally giving you NO2 and O2, right, NO2 and O2. So, this we have to establish that this follows first order kinetics. And what is the mechanism which has been proposed? This is given in the problem statement, that N2O5 gives you NO2 plus NO3 star. So, this is active intermediate. So, NO3 star gives you NO star plus O2. Now, NO star reacts with NO3 star giving 2NO2, and the rate constants K1, K2, K3 and K4. So, can explain the observed first order kinetics. So, what we have to establish? Prove that Rn2O5 is proportional to the concentration of N2O5. So, this is the typical first order kinetics we have, right. So, you see, let us write minus Rn2O5 is equal to K1 CN2O5 minus K2 CNO2 into CNO3 star. Now, this CNO3 star we have to substitute. So, what is formation of NO3 star, which is K1 CN2O5 minus K2 CNO2 CNO3 star, and then NO3 star is involved here. So, minus K3 CNO3 star and minus K4 CNO3 star CNO star, and that must be 0 according to pseudo-steady approximation, because this is the rate of formation of NO3 star. So, we can write that CNO3 star is equal to K1 CN2O5 divided by K2 CNO2 plus K3 plus K4 CNO star. Now, CNO star is again an unknown quantity. So, we have to write the rate for NO star. So, NO star is formed here. So, it is K3 into CNO3 star and dissipated here minus K4 CNO star CNO3 star, and that must be again 0. So, CNO3 star, sorry, CNO star is equal to K3 by K4 here. So, if I substitute this expression, so we will get K1 CN2O5, K1 N2O5 minus K2 CnO2 plus K3 and K4 into K3 by K4. So, here it becomes 2K3. So, combining these two, this and this, what do you get? Minus of Rn2O5 is equal to K1CN2O5 minus K2 CnO2 into K1CN2O5 divided by K2 CnO2 plus 2K3. So, this is K1 CN2O5 1 minus K1 K2 CnO2 K2 CnO2 plus 2K3. Right. Yeah. K1 CnO3 star, K1 CN2O5 CnO3 star, K1 CN2O5 K2 CnO2 plus 2K3. Sorry, here there will be no K1 because we have taken the K1 common. Right. So, you see, this is not exactly first order. If, however, this K2 CnO2 is much greater than 2K3, that is, K3 is very small, negligible, right. So, minus Rn2O5 is nearly equal to K1 CN2O5, which explains the first order kinetics as observed, right. So, lastly, so this is the overall scheme by which we can derive the example or derive the typical, this is a typical example by which we can derive the rate equation if we are provided with a reaction mechanism, right. So, that is the basic idea. Next and lastly, regarding these basics of this reaction engineering or kinetics rather, we will discuss the temperature dependence of rate constant, right. So, K is a function of temperature. So, the first model, Arrhenius equation, it states that K equal to K naught into e to the power minus E by RT, where K naught is the pre-exponential or frequency factor and E is the activation energy for a reaction, right. Because we know between the reactant and the product there is a barrier, energy barrier, reactant and the product, and the pathway is something like this. So, this is the activation energy barrier which is to be crossed, right. So, as it is minus and denominator is T, we can understand that with the increase of temperature K also increases, and it is justified through increased rate of collision, right. That is Arrhenius model. So, second is collision theory. It proposes that though the basic term remaining the same, there is an additional multiplier, that is T to the power half into e to the power minus E by RT. So, that is the collision theory, and third one is called the transition state theory, where there is also an additional temperature term being multiplied with this k naught into e to the power RT. So, in general, we will not go into the details of the theory that how they are derived, that is not our point. So, in general, k equal to k naught into t to the power m e to the power minus e by RT, right. So, m is 0 for Arrhenius model, equal to half for collision theory, and equal to 1 for transition state theory. And for Arrhenius model, you see the d phi plot ln k versus versus 1 by t, it will reduce to a straight line form, right, because ln k is equal to ln k naught minus e by RT. So, the slope is minus of e by R. So, the slope is minus of e by R. So, these are the data points. We have a fit, and we will get the slope to be minus of e by R. So, from this slope we can actually calculate the activation energy. So, that is all about the basics. In the second session, we are going to discuss about the interpretation of batch reactor data, because to model or to design any reactor, it is necessary to understand the rate equation. So, question is how to derive a rate equation, whether when we do not know whether it is a first order, second order, elementary or non-elementary, we do not know anything, right. So, under this condition, we have to employ a batch reactor, we have to analyze the kinetics by generating the data, right, and then we have to develop a kinetic model, right, which can universally represent the rate of the reaction. And once the rate equation is available, next we can go for designing the reactor. So, this interpretation of batch reactor data does not mean our focus is to design a batch reactor, but rather to derive the rate equation which will be further utilized in design of actual continuous flow reactor. Thank you.